Hello there. Today we are going to look at an experiment conducted by Michelson-Morley around 1887, which indicated that light was really unlike any other wave phenomena in that light did not require a medium for propagation. Light had been shown to have wave-like properties by Young in his famous interference experiment in 1801. In the 1890s, it was a widely held belief that light, like other familiar waves such as sound for example, required a medium for propagation. They called this media luminiferous ether and was thought to permeate the entire universe and allow light to propagate in the universe. It was also known that other mechanical wave phenomena such as sound had a higher velocity in rigid media such as metals compared to their velocity in, say, water. Since light traveled at a very high velocity in free space when compared to other media like water, it was thought that ether had to be of high rigidity to facilitate these high velocities. Yet, it had to allow massive objects like planets to pass through unimpeded, otherwise planets would spiral into their stars after losing energy, overcoming the drag in ether. So here they were, debating the nature of this rather curious media, luminiferous ether, and along came Michelson and Morley with a proposal to measure the effects of ether on light. They planned to use an optical interferometer, which was then and still remains to be the best way to measure relative change in physical distances. An optical interferometer consists of two arms, AB and AC. The light coming from the coherent source S is split between arms AB and AC. A part of the beam goes along AB and the other part goes along AC. At the end of each of these arms is a mirror. These mirrors reflect the light going along AB and AC back the way they came. The beams recombine at the partially coated mirror, and when they are going along AD, they can interfere and cause an interference pattern at a screen located at D. So you can imagine that if I change the length of either of these two arms, the interference pattern at D changes because the light would then acquire an additional phase due to the path length difference. And since this was a precision experiment, the whole experiment would be allowed to float in a pool of mercury, as you can see here, so that the ambient vibrations are damped out. Let us look at how these interference fringes behave if the whole interferometer is placed within a moving media. Since the Earth orbits the Sun, the surrounding ether would seem to move in the opposite direction for an observer on the Earth. Let's call the length of each of the arms of the interferometer d. As a consequence of classical Galilean velocity addition, in the arm AC, when the light goes from A to C, we can calculate the time that it takes to go from A to C, and that is given here. Similarly, we can calculate the time that the light takes to go from C to A again. With these two numbers, we can calculate the path length that the light took to go from A to C and back to A. So now let's calculate the path length associated with the arm AB. The time that light takes to go from A to B is just the arm length over the speed of light. So in this time, the whole system would move to the right by an amount d over c times the relative velocity of the system with respect to ether, which is v. Now, this forms a nice triangle with one side being d and the other side being dv over c, and the hypotenuse would just be half the path length that the light would have to take to go from A to B, and back to A. The path length associated with the arm AB is given here. But what really matters is the path length difference between the arms AB and AC, and that is given right here. Let us look at what happens if we rotate the interferometer by 90 degrees, going from the state in which the arm AC is along the velocity v to the state in which arm AB is along the velocity v. By analogy, you can imagine that the path length difference in this case is just negative of the path length difference that we calculated in the previous case. Now, this means that the fringes themselves moved by a certain amount. This amount can be calculated as shown here and comes out to be approximately about 0.04 in terms of the fringe widths. Notice that the arm along the direction of motion of Earth can change in two ways. If the apparatus itself is rotated, or if the apparatus is held fixed and the Earth rotates, in effect rotating the apparatus with respect to the ether wind. Such rotations would modulate the amount of fringe shift with an amplitude of about 0.04 fringe width in this apparatus. Michelson-Morley rotated the apparatus by 2 pi all the way around and took two separate measurements, one at noon and one at 6 p.m. so that this ensures that at least one arm would see a modulating effect depending on the direction of ether wind. Here is a plot of the fringe shift data collected by Michelson and Morley as they rotated their apparatus at noon and 6 p.m. The dashed line represents 1/8 of the theoretical amplitude of modulation that we calculated before, 0.04 fringes that is, and the straight line represents the experimental data. As you may notice from these two plots, there was no such modulation found. From this null result, we can infer that either there is no relative motion of the apparatus with respect to the surrounding ether, or by Occam's razor, that there is no ether. With Einstein's theory of special relativity being published in 1905, ether was no longer required to explain the propagation of light, and the null result in Michelson and Morley experiment showing the non-existence of ether became the accepted interpretation. I'll put the links to the actual paper from Michelson and Morley in the description, and I hope you have appreciated the experiment Michelson and Morley came to be known for. See you in the next How Do We Know video.